thanks so much to the organizers for the invitation to speak. Obviously, the workshop has been delayed by years, so what I was planning to speak in 2020 has significantly changed. But I'm very happy this is happening and I get to meet this awesome group of people. So thank you very much for inviting me. So I'm going to talk about a new Central Limit Theorem for what is known as the Augmented Inverse Probability Weighting Estimator. So this is a very popular estimator in the area of causal inference, and this work has been to try to understand some high-dimensional properties of this estimator in sort of newer regimes that folks in the causal inference literature have not looked at before. And this is joint work with three wonderful collaborators. So Kwanhao Jiang is currently my PhD student in Harvard Statistics. Rajushi Mukherjee is a colleague in the Harvard School of Public Health, and Shikubo is in the room, and most of you know him. He's also in Harvard Statistics. Okay, so I'll start by introducing the problem. And the basic problem is causal inference from observational data. And we're interested in a very specific estimator. So that's called the CrossFit Augmented IPW estimator. So then I'll introduce the estimator. And our goal, so this is a very popular estimator in that this estimator has really nice properties that have been studied before in the literature, so it's something that is very widely used. So our goal was to see, can we analyze this estimator in some high-dimensional settings without assuming traditional sparsity-type conditions. So the literature before our work basically assumes sort of sparsity or ultra-sparsity kind of conditions and underlying regression coefficients in the problem. And if you have these assumptions, I'll introduce some nuisance functions in my problem. If you have these assumptions, what happens is all the nuisance functions in your problem, or at least some of them, you can always consistently estimate. But we wanted to sort of push this barrier and see that, do these estimators still continue to have nice properties when these assumptions fail to hold? And I'll give you some sort of experiments to demonstrate what are some examples of settings where these assumptions can really be valid. So that's the goal in this work. And there's only one single result, which took us, unfortunately, many pages to prove. It's a new Central Limit Theorem. And what I'll try to focus on more is to sort of say what is the main proof difficulty. So we are using tools that, folks in this audience are very familiar with, but it just turns out this kind of causal inference-based estimators raise new challenges which we sort of have to navigate. So I'll try to explain why those challenges arise a bit, and then we conclude with the applications of future talks. Okay, so what's the basic problem? We observed a sample of size n. I'm assuming IID for the moment. The folks at the back here, okay? Okay, so my data looks as follows. I have three kinds of variables in my data. My outcome is yi. I'm assuming that to be real value for the stock. I have a treatment variable that I'm assuming to be binary for the stock, and then I have some p-dimensional covariance. Okay, so what you're supposed to think about as a running example is AI equals 1 probably indicates that you assigned a particular drug to someone, and 0 indicates you did not assign the drug. And then what you're interested to estimate is the effect of this treatment on the outcome. So did whatever you're being treated for, did that get cured, did that improve, etc. So that's what you're measuring, that's your yi's. Now, this is a very difficult problem on its own because, okay, how do you estimate such quantities? So there have been sort of multiple languages that have been developed to answer this question, and one of those entire language is based on graphical models. So you can use sort of directed acyclic graphs to understand various kinds of causal relations between your underlying variables and try to answer this question. That would have been the natural connection to this workshop, but I'm actually not going to use that language and use a different language instead, which does not have graphs explicitly, but these two languages are sort of, they're connected to each other, basically. The language I'll be using is that of potential outcomes. So let's focus on one individual, the ith individual. Now, before I perform my experiment, this individual has some outcome, yi1, associated to what would happen if you assign the treatment, and has a corresponding outcome for if you didn't. And the point is, in my data, I only observed one of these two. I don't get to observe both. Okay? So potential outcomes is the name for what would have happened to the same person. Now, because I don't observe both of these, it's going to be a bit challenging to estimate anything. But if I define my potential outcomes, then I can actually formulate this question mathematically very well. So the mathematical formulation of can you estimate this? Okay, then what am I trying to estimate? You can try to estimate things like the average treatment effect, which is simply saying I want to estimate the expected value of the difference between the potential outcomes for somebody. And you could do this at a conditional level, so there are all these different, so this is your parameter of interest for answering this question. But obviously, because for the same person I didn't observe both of these, this is unidentifiable from observational data in general, right? And what I would like by identifiable, I would mean that, okay, can I express this as some function of my data distribution? You cannot without further assumptions. So there is obviously an entire literature on what are basic assumptions you need so that this parameter becomes estimable from the data you've observed. And so I'm just laying out these basic conditions because, this is sort of set of conditions you always need. There is a causal identification literature that is about testing these conditions and stress testing them, but we are talking about settings where, let's say, these conditions hold. I'm not going over them in detail. Then the average treatment effect, which is defined in terms of your potential outcomes, which I didn't get to observe both for the same person, can be expressed as, difference between expected value of yi given ai is 1, xi, and the corresponding. So the right-hand side of this equality is in terms of conditional distributions of the observed data. So this is something that you can hope to estimate. So our goal is to basically estimate this quantity. Okay, and then I can forget about the causal language, right? This is just a well-defined parameter. Okay, cool. So that's our goal. I want to estimate this parameter. And now there is extremely rich literature in this area. And if I want to take a high-level view and understand what has been happening in this literature, then the first thing you'll notice is there are two quantities that are of fundamental importance, which I'm not seeking to estimate for my eventual goal, but they just arise along the way. Okay. So one of them is the propensity score function or model, whatever you might call it. This is just in this case, it's just the distribution of the treatment given the covariate. So in this case, it's just, because it's binary, it's just probability of ai equals 1 given xi, right? And the other one is the outcome regression model, which is what is the conditional expectation of your outcome given the treatment and the covariance. So typically, yeah.
Here the notation is I of x is conditional expectation given xi equal x.
I'm just saying given xi because I'm not doing.
But on the left-hand side.
Oh yeah, yeah. Oh, sorry. Yeah.
So the next question is the next line.
Yeah.
Given ai equal.
Yeah. So this hides two functions. One of them is like m1.
Just wait.
Yeah, m1 which is a equals 1, and the other one, but I just didn't want to introduce it. This is xi equals x. Okay. So these are my nuisance functions. Now, broadly, this literature can be divided into three parts. So the first one is I have these two functions to estimate my average treatment effect. I could just think of modeling these propensity scores as best as I can and develop estimators based on that. So that's a literature called inverse probability weighting. There is another literature that focuses on modeling this function well instead, and that's what's known as G computation. So this is a literature that really focuses on this second function and then develops estimators of the average treatment effect based on that. But turns out, if you do this, you sort of don't exploit your problem structure as well. And the reason for that is you actually have other nuisance functions if you only model one of them. It's unclear when you do really well with just modeling one of them. So obviously, the very smart people have been working in this area, and a lot of sort of prolific works from Harvard. So Jimmy Robbins is in Harvard. So there is a different literature that introduces a special class of estimators that tries to exploit the best of both these scores. And I will clarify in a bit what I mean by that. So this class of estimators is what is known as augmented inverse probability weighting. So it takes your inverse probability weighting estimators, which try to estimate pi, and does an additive perturbation to that is created in a very structured way, such that these class of estimators has some nice robustness properties when your underlying models might be specified, which is obviously what is more of the reality in practice. So let's see what are the properties of the. So for this talk, this is what I'm going to focus on, this class. I'm going to basically first introduce this class of estimators and then talk about its sort of most basic fundamental properties. So let me introduce these AIPW estimators. Okay, that's the acronym. I am introducing it in a way so that we do like a leeway into our work. You could have multiple versions of this, but let me first start with a simple version. So what you could do is you have two nuisance functions, and then your ultimate goal is to estimate the ATE, as the average repeat effect. So you could split your data into three parts, let's say three good parts. You estimate the two different nuisance functions from two different parts. I'm doing data splitting because if you're in very high dimensional settings, if you estimate everything from the whole data, there could be various sorts of issues. So there is sort of literature on that, so we're not going to do that. And then to obtain your final estimator, the final estimator is computed on the third part, which you haven't used yet. The final estimator is difference of two terms. And the first term looks as follows. So recall AI is my treatment variable, YI is the outcome variable, and pi hats are my estimates of propensity scores from the first split. Okay? So if I just took difference between these two terms, I would get what is known as inverse probability weighting. Okay? So nothing about the outcome regression estimator is here. It's just the estimated propensity scores. But now there is a second component which includes this outcome regression estimators. And the structure just falls out of some basic calculations. But the structure is super important. Like exactly what these coefficients are, that's actually super important. And I'll see in a bit super important for what. Now, as you can see, I could do many variants of this. So for instance, I could split into two parts, calculate nuisances, all the nuisances from one part, and calculate this final step from the other part. That was one choice. Or you could not split at all. That would lead to difficulties, but we are going to focus on this 3-split version for this talk. So this is the basic estimator, difference of two quantities. And the 1 is for everything for the treatment group, and the 0 is for everything for the control group. Alright, so now I want to keep some notations on the board, because this will be crucial. So in this talk, when I say tau hat of S sub A, the picture is I have three parts to my data and I give them names. So this means first argument is the split from which you calculated your propensity score estimates. Second part is the data split from which you calculated the outcome regression estimates. And third part is from where you calculated your average. Okay, this will be important, so let me keep that. Now, what is the most fundamental basic property of this class of estimators that makes them sort of super appealing? Basically, and I'm shoving many things under the rug, but roughly, if you look at square n times this estimator minus your parameters, this is my average treatment effect, then you have sort of first order terms that are Gaussian fluctuations with some variance. But then if you look at the error terms, they become product of error in estimating your outcome regression M and error in estimating the propensity scores phi. So what that means is I could estimate one of these super well and do very poorly on the other. Still my this product is going to be small. So that's the main idea. And that's why, the additive perturbation that was added to this estimator, the structure of that was important. And because of a decomposition of this sort, sort of in the classical literature, Sharfstein et al. And Bang and Rogans, they were able to show that
this class of estimators is actually square root n consistent and asymptotically normal, even if one of the outcome regression or propensity score models is misspecified, and this is what is known as the double robustness property of these estimators. And this became sort of a very big deal because obviously everything is misspecified, right? Okay, so this is why this is an interesting estimator. Now, this is all low dimensional stuff. So dimension is fixed here and sample size is going to infinity. And obviously there's been a lot of work in the high dimensional space trying to understand properties of these estimators. And especially for causal inference problems, high dimensional problems are even more important because the more covariates you have access to, you sort of want to include all of them in your model because that's in some sense a good bet for getting away from unmeasured confounders, or that's at least the logic that's given. And there has been a lot of work in trying to extend this double robustness feature. Maybe the unifying theme of all of these prior works has been they allow potential misspecification in one of the models, but at the cost of very strong structure on the other. So one kind of structure that's always assumed is like one of these nuisance models has to be very, very super sparse. You can be in very ultra high dimensions, but one of these objects is super sparse, and that if you have a regression model there, the underlying coefficients have very little number of non-zeros. So that has been a limitation. And I'll try to motivate why this is a limitation with sort of a picture that many of you here are familiar with and uncovered for the first time. So I'm running a very basic simulation here. My number of features is 700 and number of samples is 10,000. So as you can see that this ratio is not even 0.1, so it's very low. What I'm doing is I'm taking this AIPW estimator and I can estimate its variability numerically, right? So I'm taking sort of features that are already Gaussian. I could change that to some other sub-Gaussian tail distribution that wouldn't matter. And I'm taking my propensity score model to be a basic logistic regression model, my outcome regression models to be linear models. And I'm allowing the underlying coefficients for these models to be not so sparse. So maybe a fraction of them are zero, a fraction of them are zeros, and the other fraction is non-zero. And they could be coming from some distribution. They could be IID from some distribution. So what you see here is this is the variability of this estimator when we run this simulation and just estimate it numerically. But the prior theory is going to tell you the CLTs for this estimator. It's going to tell you that the estimator variability should actually be given by this red line. And so as you can see, so this is high dimensional variance inflation, that the true variance is actually much higher than what the prior theory tells you, because if you have very ultra sparse assumptions, then effectively the final results end up looking like low dimensional results. And so we were interested to understand or explain this picture for this class of estimators that are not like regression estimators by themselves, but actually they are two-stage estimators. So I'm estimating different regression coefficients and then I'm doing a plugin for a downstream task. So we were generally interested to understand for these two-stage estimators, how can you build the theory that explains this picture? And so, of course, this has been understood for, some high-dimensional problems, but these kind of causal inference-based two-stage estimators for that is AIPW. Okay, so that's our goal here. The question is, can we analyze a commonly used version of the AIPW in such a high-dimensional regime in that it captures this picture going away from sparsity-type conditions? Now, I have to explain to you why I suddenly use the term commonly used version of AIPW, because I already introduced one estimator. But this probably means that that estimator can have many different versions. So let's recall what was the basic structure, split into three parts, and then, compute each of the quantities from a different split. But from statistical efficiency perspective, we don't like sample splitting, right? We are losing sort of the amount of data from which we are calculating our final estimator. So obviously people don't do that. What people do is the natural thing to do. After I compute this estimator, I could switch the roles of all these folds and recompute my estimator. So the second time I could maybe instead do outcome regression from here and propensity score from here and ATE still from here. and I can do all these possible permutations. So that's what people do in practice. They recompute the estimators, switching the roles of the samples, and average everything that you obtained. That version of any estimator is known as the cross-fit version of that estimator. Okay, so in our case, in this picture, then we have 3 factorial, what I will call pre-cross-fit estimators, and then we average them. Now I want to point out something that was known in the prior literature that made understanding these cross-fit estimators sort of similar to understanding each of these estimators, and that is the following phenomenon. That first of all, let's think of the case when the third split is fixed and I switch the roles of the first 2. So I'm just switching the roles of where I'm computing from, which nuisance from. That one doesn't matter because from a low-dimensional perspective, if my third split is the same, they're effectively the same estimator. But the split from which I am calculating my average treatment effect estimator, if I change that choice, in the prior literature, the covariance between any 2 such estimator is still going to be asymptotically negligible at a square root n scale. Okay? And that means when I average, I take variance of this guy, it just becomes, sum of these variances roughly. And that's nice because you lost some efficiency because of sample splitting, but then there are proofs that you recover back exactly that efficiency. So that's why cross-fitting is popular. This motivates us to study this cross-fit AIPW. Okay. Now, let's think about if I want to extend an analysis of this kind of estimator in some high-dimensional regime without assuming underlying sparse structures, what are the challenges? So the first challenge is, if you don't have underlying structure, then neither of your nuisance parameters could be consistently estimable, because all the prior theory uses one of them being consistently estimable. And we have all these pre-cross-fit estimators, so you have to track their joint distributions, and even if you could magically show that that joint distribution is a multivariate Gaussian, you still have to calculate the variances. And it turns out the cross covariance being negligible no longer holds, so you have to calculate those covariance terms also. In particular, if I switch the role of the third split, then this actually may not be trivial. Okay, this might have contributions. And we have binary treatments, so that involves, you have to estimate propensity scores, so there are nonlinearities involved in these models. So that makes sort of existing literature, there is some related literature in econometrics on linear instrumental variables models that sort of makes that hard to directly import here. So basically we need tools that tackle all of this, and my goal is to build things that's going to apply to dense signals as well as some kinds of sparse signals. Okay, so this is okay. So we are able to do this in some stylized settings. So what's the formal setting? I'm going to assume a logistic regression or logistic type link function connecting my treatments with the covariance. Okay, and just linear models for the yi. So here you can see for AI equals 1, you get a certain linear model, and AI equals 0 is a different linear model. And they allow the variances to be different for these errors. And in this setting, your average treatment effect is just going to be the difference between the parameter alpha 1 minus alpha 0. Okay. Now we are going to approximate this picture we saw by this high-dimensional scaling limits. And obviously, they have been very, very popular and looked across diverse disciplines. I said our settings are stylized in that we're going to start with standard Gaussian designs, and then we're going to try to understand how much we can push the Gaussian-based theory in these kinds of problems. And we have conditions on sort of signal-to-noise ratios in the underlying models of this sort. So let me focus on one of them. So I'm saying if I look at my propensity score model, then norm of beta square properly scaled goes to some constant. Whenever I say goes to something, I mean this is something finite and bigger than 0. Okay. But the other way to interpret this is the same as variance of xi transpose beta, which is in some sense the signal-to-noise ratio of this problem. Okay, so we need to hold this finite, otherwise that's going to diverge, and then the problem is going to be trivial. So the main difference between our work and prior settings is, in this setting, like the full p-dimensional regression vectors may not be consistently estimated. However, our ultimate goal is the average treatment effect, which is just a scalar, right? So we may not care about whatever nuisance parameter arises along the way. If that is high dimensional, I may not care about estimating the full thing consistently, and the downstream task might still be okay to do that. So that's sort of the message we will see. Okay, now lots of heroines in this setting, and also folks who started this area in different subdisciplines. We can almost name subdisciplines where the scaling limit has been studied a lot, many topics or many subjects. But for this work, actually, the more related works come from the econometrics literature, where this kind of scaling limits are referred to as many regressors, asymptotics. But as I pointed out, they have the entire theory on how do you tackle such estimators when you have linear instrumental variables models, which is slightly different from what I'm doing, but still two-stage kinds of estimators. But they use linearity very, very crucially, so they don't have the sigmoid type of limit function there. And more recently in high-dimensional statistics, in 22, sort of a month before our work was posted, Yadlowski compared some of these causal-based estimators to sort of some first-order properties, sort of what is the bias, what is the variance, these kinds of questions, but there is no central limit theorem. Okay, so this is our main result. Maybe before I actually describe it, are there any questions? Okay. So what we show is the following. So consider this estimator that I already introduced. Then if you're estimating either both your outcome regression and propensity score models using things like maximum likelihood. So when you're doing that, you have to make sure that the ratio P over N is diverging to some positive constant, but it has to be below a certain threshold so that the maximum likelihood estimate still exists. So either when you're estimating both in this way, or you're estimating your outcome regression using maximum likelihood and propensity scores using ridge regularized logistic loss, for instance. Then this cross-fit AIPW, it's square root n consistent and asymptotically normal, and we characterize both these variances. Now, I won't write the full variance formula because it's sort of very, very complicated, but I'll try to explain what are the differences of this term from the classical term. So this is our variance formula. Now, the second term is variance of these covariates times beta 1 minus beta 0. So beta 1 and beta 0 are the underlying signals in my two outcome regression models corresponding to the two arms. Okay? This term shows up classically. So this term you can interpret as sort of difference in these models, underlying differences, and that shows up classically. But the difference actually lies in this first expression. Now let me read that off a bit. The coefficient here is sum of the variance of the errors in your outcome regression model. So this coefficient is coming from the noise in your outcome regression model. And this function that I did not write fully here is coming from your propensity score model. So this is a function of kappa. Kappa is the limit of the number of features to number of samples. So that is quantifying how high dimensional we are. It's a function of gamma. Gamma is the underlying signal to noise ratio for my propensity score model. And if you use ridge regularized regression for your propensity scores, it's also a function of your tuning parameter. So the first thing to notice is the contribution from the outcome regression and propensity score model sort of decoupled. So the outcome regression shows up here and in this coefficient, but not over here. Now the classical formula looks exactly like this. Exactly like this. Except this quantity is actually quite a bit different. Okay? So what I'm going to do is I'm going to zoom in and try to compare, let's say, this quantity between our, what happens when kappa is positive, kappa is a ratio of P over N, versus, let's say, when it is 0. So to compare this, Now I'll need my notation that I introduced at the beginning. So this was my usual encoding of the different estimators. But based on this notation, I can divide my 6 estimators into 3 different pairs. And the way I divide them into 3 natural pairs is if I fix the split from which the average treatment effect was calculated and switch the roles of the other 2, that gives me a pair. And that's sort of natural in that you're calculating your final parameter from the same split, but just switching the roles of the other 2 from which the nuisances were calculated. So let's just call that they are siblings. Now, the total variance of this CrossFit estimator has a nice variance decomposition. So sum of the variances of all of these estimators plus the covariance between estimators that belong to the same pair that are siblings plus covariance between estimators that come from different pairs. Now, the difference with prior literature is that this last term is going to be negligible after proper scaling if you are in either low dimensional regimes or ultra high dimensional sparse regimes. But this is going to have a non-trivial contribution in our regime, and the kind of contribution it has actually raises some interesting questions, and I'll show that in a bit. And as one would expect, the first 2 terms are much larger than the prior setting, but that is something you expect. That's a basic high-dimensional effect. That's the variance inclusion effect. Okay. So you just expect these variances, their contributions to be much larger than these settings, but that's something you expect. Okay. So any questions on this decomposition? Now, we can illustrate that through sort of very simple pictures. These 2 pictures are simply plotting the logarithm of our formula versus the classical formula for these terms, respectively. I'm sorry the font is not very visible, so let me read things out for you. On the x-axis, you have your dimensionality factor, that is just the ratio of p over n. And on the y-axis, I told you we're plotting this log. And you expect these to rise, like how you see here. The different curves are for different signal to noise ratio values. Okay. Now, the interesting thing is, when I go to this last term, its classical value is 0, so that's the red line. But in our regime, this term, if you choose your nuisance estimators properly, it can be made negative. So the important takeaway here is, when I'm looking at the total variability of this estimator, if I only had these 2 terms, the variance would be much higher. So, an applied statistician might come and say, why would I look at this theory? Because my variability is becoming so high, that's going to make this estimator I like very much pretty much useless. It's going to say that, oh, this has no preciseness, so I don't like this theory. But the interesting thing is you can estimate your nuisance in a way so that you start driving this back down using these covariance terms. And this is sort of a beauty or a new phenomenon that you start seeing when you have these 2-stage estimators, where you have some degrees of freedom in how you sample split to estimate your nuisances and what choice of nuisances do you use there, and then you're using this average. Now, this is sort of blessing of high dimensionality for cross-fitting. And right now we understand this problem to the extent that, we can choose nuisances to actually observe this phenomenon, but we don't have a full characterization of this is a necessary sufficient condition on your nuisance estimators that will ensure you have this negative covariance phenomenon. So the final takeaway is then I can go back to my applied statistician and say that, hey, this is not the only story. There is a second part of the story. So the final variance is going to start looking close to what you liked. But you still have high dimensional guarantees without structure on underlying regression coefficients. So maybe this is something you shouldn't throw out the window just because the variances of the first 2 terms are very high. Okay, so that's sort of the underlying picture and sort of a new phenomenon you start seeing for 2-stage estimators. And so you can see there is a stark difference in behavior in our regime versus classical. Just a quick pointer, the classical is going to collapse to this point on the left where by n equals 0, and then we go back to what the classical value is. So these are logs, so it becomes log. Okay, basic sanity check. So we should maybe start doing simulations in settings where our assumptions hold, so we don't become too cynical. So this is a setting where our assumptions hold. It's IID Gaussian designs. We are plotting sample quantiles versus theoretical quantiles of the estimator square root n times the estimator minus the parameter. So the darker blue line is what our formula gives, and the classical formula will give you the cyan line, but we actually want to be on the 45-degree, aligned with the 45-degree lines. The left-hand side is the estimator we studied, but the right-hand side is a version where you trim the sigmoids. Whenever you see a sigmoid in the formula, you just trim it because otherwise the tails are going to go back. So this is sort of basic sanity check. But there are other interesting questions that come up along the way. So the first question is, because you have these nuisance functions, there are lots of choices in how you could estimate it. And then the question is, can I sort of design optimal nuisance estimators? So I want my downstream variance to be as low as it could possibly. So we investigated this a bit, and the standard strategy in this literature is to choose your tuning parameters doing some sort of cross-validation. But if you use something like, let's say, leave one out cross-validation, which has nice guarantees even in high dimensions for the prediction error, and if you look at a plot where on the x-axis you're varying your tuning parameter, and on the y-axis you're just looking at the variability in your estimator, then that goes like this and then goes up. But the best value of the variance is over here, and cross-validation based something is going to give you a value over here. So, this is not surprising because these things are sort of optimizing for the prediction error, but that is also to say that we could maybe build better tuning parameter selection strategies like specifically focused on inference questions. And one way to do that is if we had an estimator for the variance in our formula, then you could just optimize that and choose your tuning parameter. So we don't have that full theory yet, but this is sort of raising that there are interesting inference versus prediction questions in terms of choosing tuning parameters that sort of show up in this book. Okay, now we're stress testing our assumptions, and we believe in universality because Laura already gave a talk trying to convince everybody that you should believe in it, and we have many, many people in this room who have sort of exemplary universality results. So this is my first sanity check. I'm changing the Gaussianity in my design distribution. So what I'm doing is, and I'm also starting to go away from my ID assumptions on my design distribution. So what I'm doing here is, for the design distribution, the jth feature, I'm going to make it discrete, take values on 0, 1, and 2 with certain probabilities. Okay. I mean, these are inspired by designs that people kind of see in genetics type problems, but there's still a choice simulation. And then they're suitably centered and scaled. We're using the same Gaussian formula, and you see a picture like this. There are more deviations of the tails, but if you inserize again, you see a picture like this. We don't have a formal proof of this yet, but the paper is a major revision at the annals, and as you can imagine, you've been asked to, prove something about this, so we're trying to do that. Now, the other way you could obviously push the stylized assumption of the design is, I'm starting to introduce correlations, which is natural, and then how much of this theory holds. So, I have maximum likelihood estimates and nice regression problems, so I could actually, if I just focus on maximum likelihood estimates and Gaussians, my problem is rotationally invariant. So there, it's very easy. So the IID and the correlated thing are going to be just exactly the same. All you have to change is what's the definition of signal to noise ratio in your formula. And you can do that. And these are pictures. On the left-hand side, this is when your covariance matrix is equally correlated. On the right-hand side, when you have an AR1 model. So there's a different formula, but adjusted naturally for what is the signal to noise ratio if you have a covariance matrix. But if you use sort of regularized estimators for one of your nuisance functions, the same thing is not going to hold. There will be challenges, but there has been a lot of theory trying to address those kinds of problems in vanilla regression problems. So there is some hope that that possibly can also be done. Okay, so our theoretical workhorses are all things that all of you are very familiar with, but we use a few different techniques. The first is just the basic cavity method, but the way you use it is to decorrelate dependencies in various terms. But what will turn out that if I just do basic cavity method, it's not going to go through. Because the estimator you're studying is pretty complicated. The second tool is approximate message passing theory, which is a very nice tool whenever I have sort of nonlinearities in my problem, but I still have convexity, estimators that are solutions to convex optimization problems and nice exponential families, etc., etc. I can build the corresponding in the algorithm to track sort of bulk properties of those estimators. So what I mean by bulk properties is something we will need to build theory for is if beta hat is, let's say, my maximum likelihood estimate or ridge regularized ridge regression in the logistic model, then what's the limit of this norm property scale then? So AMD theory sort of gives you that directly, and those exact values sort of come out of my earlier thesis work. But we also have lots of quadratic forms that show up, and the whole deterministic equivalence machinery from random matrices is super useful there. So in the remaining few minutes, what I'm going to try to do in a couple of slides is the novelty in this work has been more to figure out how do we decorrelate lots of different dependencies. And I want to try to summarize in one slide sort of why that was difficult here. And we use these tools. I mean, for the deterministic equivalence, there was nothing that could directly apply, so we had to basically prove everything, but the tool was still there, and the tool sort of applied. And for the AMP also, the results were modifications of earlier results for high-dimensional logistic models actually. So before I say that, people might have seen cavity method in different hoods. It's sort of a diverse audience. What I want to do is for this basic regression setting, I want to just say, how does cavity method work? So recall my estimator. So what was my estimator? I had these three crossfit estimators, and I have sums over these guys being all possible permutations and 1 over 6. That was my entire estimator. But because I'm including all of these guys in this summation, then in one of them, I have, let's say, the ith covariate from the first split, and somewhere else, let's say I have the, estimate of propensity score model. So this could be the maximum likelihood or ridge regression in logistic model. So I have both in this complicated expression. And they're of course dependent because the ith sample goes in the computation of this estimator. So something that you can try to do is you just leave the ith sample out and recompute your estimator. So this is your leave-in observation of estimator. And this guy is going to be independent of the ith covariate. That is basic cavity method in this setting. But it turns out these problems are super nice in that the estimators I'm using here, they have some first order stationary conditions that they satisfy. So I can write out the stationary conditions for this full n observation estimator. I can write out the stationary condition for this n-1 observation based estimator. And it turns out if you subtract these stationary conditions and do some massaging, then roughly you will get a relationship like this. So this guy is very complicated. It involves all my n samples, but through a relatively complicated function, obviously I'm showing some difficulty under the rug, I've basically decoupled roughly the dependence on the n-1 observations and the ith sample. So on the right-hand side, because these guys are independent, the right-hand side is sort of easier to handle than the left-hand side. What this function is going to depend on whatever your problem parameters were, etc. So the particular form is going to vary from it. Okay, so now that's good. That's basic cavity method if I have one regression problem, one estimator. Now, so what do we have in this problem? So in this problem, because my estimator is average of all of these things, if you look at the expression, then all terms of the form xi transpose beta hat shows up, where I is an index belonging to any of these splits, and k is an index belonging to one of the others. So these two are independent, but they all show up together in my estimator. So which means I'm going to have this crisscross dependencies, right? So for instance, I have xi transpose beta hat SB somewhere where I belongs to SA, and I have xj transpose beta hat SA somewhere where j belongs to SB, and these are dependent and these are dependent, right? And all possible choices of these shows up in the expression. Now the issue with that is that every time you do a cavity trick, there is an error you incur. Because when I do this approximation, there are error terms here, right? This is not exact, there are some error terms. So the issue is, you can decorrelate the pairwise dependencies, but for a central limit theorem, because all of these show up, you have many of these error terms, and obviously they accumulate, right? So then you have to do very careful analysis to track their contributions and figure out which of the terms are finally going to contribute and which you can sort of ignore. So our hope in this work was to maybe build something which can be useful for studying other such two-stage estimators. For any these kinds of estimators, you will have a similar problem. We hope we have been able to do that to some extent. But it was still a stylized setting, so I'm not going to claim that we have a full machinery that you can just apply right off the bat, but we hope that in sort of the 100 pages of proof, just to overcome this difficulty, there are nuggets that can be useful when in other settings where you have lots of too many cavity equations and you need to track the error terms here.
Is the quality for approximation of f is depending on Taylor expansion of f?
So, sorry, so that
Is the
again.
quality for approximation of f depends on the Taylor expanding f?
Sorry, equality of.
So the error between
Right.
the left and side what controls this error? The
What controls the error?
Taylor expansion of f, or there's something else?
So it's not the Taylor expansion of f per se, but when I subtract these stationary conditions, so I have let's say, can you see there if I write?
Yeah.
Okay, so so this is gradient of, let's say, my log likelihood. So if my log likelihood is dependent on n observations, the beta hat SA satisfies something like this. And the issue is I can't really directly do linear expansions here because I don't know what is close to what. But what I know is that both of these satisfy two equations like this. Now the issue is, so this is the n-1 sample base, and this is the minus of it. Now you could subtract this and you get something, right? You get some equation. But the issue is we have these logistic models floating around where within this log likelihood there are terms of the sort log of 1 plus e to the, let's say, xi transpose beta hat. And the issue is that, the errors come from sort of Taylor expanding this object. Because I want to basically take this thing out and have sort of functions of that so that I can ultimately get to an equation like that. So F just pops out from the calculation, but the errors are coming more from Taylor expanding this in some sense, sort of from. I mean, if I had linear models, I would have had xi transpose betas outside, and that would have been simpler. Right. Okay, but then obviously then tracking the errors means sort of when I'm doing those expansions, the errors are functions of some, third order functions of xi transpose betas and tracking all of tracking. Okay, so with that I'm going to wrap up. So what I presented is sort of a new central limit theorem for this cross-fit AIPW estimator, and you're trying to build something without when I may not have consistently estimable nuisance parameters in either of my nuisance models. We obviously see a variance inflation phenomenon here, which is expected, but we also see this interesting phenomenon that you can have covariance terms that can cancel out the higher variances. There are lots of questions that can emerge from this. Obviously, two-stage estimators are not just something that's used in causal inference. There could be other problems too where they might be interesting. And anywhere you have nuisance functions in your problem, you might be interested in something like this. But the other thing that was interesting is because these covariances are negative, then one can ask things like, what is the optimal sample splitting strategy? Because you can imagine I can keep on sample splitting and then negative covariances will start cancelling out. So there's something about what is the right way to sample split and then average. And obviously you could ask other, sorts of other interesting questions about other nuisance estimators, etc. Okay, so I'll wrap up with that. Thank you for your attention.